Hi everyone, and welcome to RUBIN'S Mind Lab, where we break down the latest research into what it really means. Ever wonder if the words we use have a hidden impact on how well computers understand meaning? Well, this new study dives deep into that, and it might just change how we think about testing artificial intelligence. So imagine these computers can now represent words as a bunch of numbers in a special space, kind of like giving each word coordinates. This is called distributional semantics, and it is super useful for everything from search engines to AI assistants. The big idea is that words used in similar ways in language probably mean similar things. But how do we know if these computer representations of meaning are any good? That is where this clever test, the vocabulary multiple choice question, or VMCQ, comes in. Think of it like a vocabulary quiz for computers. You give the computer a word, and it has to pick the best synonym from a list of choices, kind of like a game. The researchers here wanted to see if they could make these tests even better, especially when it comes to understanding how word frequency, meaning how often a word is used, affects how well these computer models understand things. Now, these VMCQ tests have been used for a long time to test how good humans are with words. The idea is that if a computer model gets the right answer on these tests, it means its numerical representations of words are pretty accurate. But the scientists noticed something interesting. They realized that tests designed for humans might not be the best for testing these computer models, especially because computers can process way more information than humans ever could. So, their main goal was to figure out how to design VMCQs that are perfect for testing these computer language models, not just borrowing ones made for people. They believed this would give much clearer and more reliable results, especially when looking at word frequency effects. First, let's talk about how these computer word representations, called distributional semantic vectors or DSVs, are made. They're usually built by analyzing massive amounts of text like books and websites and counting which words appear together. The more words appear together, the more similar their numerical representations become. The researchers wanted to zoom in on word frequency. It is something we all know matters in language learning. We learn common words faster and know them better. They suspected the same might be true for these computer models. But the problem was that previous tests weren't clear enough about this. They started by looking at the best ways to design these VMCQ tests to study frequency effects. They tested a specific VMCQ designed by Levy and colleagues in 2017, which tried to control for things like word length and frequency to isolate the effect of stem word frequency. They even had humans take these tests to get a baseline. For humans, the results were pretty clear. Higher frequency words generally led to better performance, which makes sense. But when they applied this same test to 9 different computer models, things got weird. Some computer models did really well overall, even better than humans, but here is the kicker. Instead of showing an advantage for higher frequency words, many of these computer models actually performed better on lower frequency words. This was the opposite of what they expected. This unexpected low frequency advantage for computers was the big mystery. It suggested that the way the VMCQ tests were designed might be messing with the results. So, the researchers decided they needed a whole new way to design these tests to get to the bottom of this. Their first big discovery was about the distractor words, the incorrect options in the multiple choice questions. They found that the choice of these distractors had a much bigger impact on the computer model's scores than anyone thought. It was almost like picking the wrong set of wrong answers could fool the computer into looking smarter or dumber than it really was. They showed this by testing the same computer models with tons of different sets of distractors for each question. As you can see in this graph, the scores bounced around a lot depending on which distractors were used, especially for models that weren't already scoring perfectly. This meant the original results from Table 3 needed to be taken with a grain of salt. So, to fix this, they came up with a more robust way to measure performance. Instead of just one set of distractors per question, they developed a method to effectively average the results over millions of possible distractor combinations for each question. This is called the D600 method, and it makes the scores much more reliable. When they retested the computer models using this new, more reliable D600 scoring method, the results started to look more sensible. While the overall scores were similar, something changed when they looked closely at the frequency effects. The real breakthrough came when they started digging into why the original test caused that weird low frequency advantage. They realized that the original test design had a hidden bias. It often picked the higher frequency word as the stem, the word to be defined for high frequency questions, but the lower frequency word as the stem for low. Frequency questions. This meant the computer was sometimes being tested on easier pairs of words, even when it was supposed to be a low-frequency question. They discovered that the quality of the stem words representation was super important. Lower frequency words, when used as stems, tended to have further distances to distractor words. This made it easier for the computer to pick the correct synonym because the wrong answers were further away in the numerical space. even if the high-frequency words were generally understood better, by carefully controlling which word in a synonym pair was the stem and which was the synonym. And by focusing on the synonym's frequency, they finally got the results they expected. This improved VMCQ design, where the synonym always had a lower frequency than the stem, and the split was based on synonym frequency, showed a clear high-frequency advantage for almost all the computer models. The weird low-frequency advantage vanished. So, what is the big takeaway here? The researchers have come up with a much better way to design VMCQ tests for evaluating language models. The key is to be really careful about how you select your words, especially the distractors, and to make sure you are consistently measuring the effect of synonym frequency. This new method is more reliable and gives a clearer picture of how well these computer models truly understand word meanings, especially when it comes to frequency. Now, what does this mean for us, for humans? The study suggests that while humans also benefit from high-frequency words, the computer models experience something different due to the limitations of the test design. It is a reminder that while computers are getting very good at language, how we test them matters a lot, and their understanding might still be quite different from ours. The researchers also touched on semantic ambiguity, meaning how words can have multiple meanings. They found that for these computer models, ambiguity didn't seem to be the cause of the weird low-frequency advantage in the end. This research is a great example of how we can refine our tools to get better answers. By meticulously dissecting the VMCQ test itself, the scientists were able to overcome an anomaly and develop a more robust method for understanding how word frequency shapes computer language models. It's a subtle but important step in building better AI. So, what do you think about this? Does it change how you view AI understanding language? Let me know in the comments below. If you enjoyed this dive into the fascinating world of computational linguistics, make sure to give this video a thumbs up, subscribe to RUBIN'S Mind Lab for more science breakdowns, and hit that notification bell so you don't miss our next exploration. Thanks for watching, and I'll see you in the next one.